Welcome back. In this session, we'll tackle the problem of high-resolution image synthesis, building a system that can generate images that are not only realistic, but also highly detailed and diverse. This task has enormous practical value, from art and design tools to virtual worlds and gaming, to AI-assisted creativity like text-to-image generation. The ability to produce photorealistic, high-resolution visuals on demand is becoming one of the most exciting frontiers in generative AI. But achieving this is far from trivial. Traditional generative models like VAEs and GANs have been incredibly influential, but they run into serious limitations when we scale up. Issues like posterior collapse, poor diversity, and difficulty maintaining fine details. To push beyond these limits, we now frame the problem as a sequence modeling task, inspired by breakthroughs in NLP. The key innovation is to tokenize images into discrete visual units, just like words in a sentence, and then use a transformer-based autoregressive model to generate images token by token. This approach makes it possible to capture global structure, fine details, and scale up to very high resolutions. In this video, we'll walk through the requirements to clarify the data preparation steps, the two-stage architecture of tokenizer and generator, how to train and sample from the model, and finally, how to evaluate and design the full system pipeline. By the end, you'll see how cutting-edge systems generate stunning, high-resolution images with remarkable fidelity and control. The problem is to design a system to generate high-resolution and realistic images. Here are some good requirements to ask any categories of images to focus on. What kind of training data do we have? Shall we support additional conditions such as text descriptions? What resolution range do we want? Is there any real-time requirement? This system is designed to generate high-resolution images based on a user's request. The input is a prompt or specification describing the desired image, and the output is a high-quality, detailed, synthesized image. Traditional generative models like variational autoencoders, VAEs, and generative adversarial networks, GANs, have been foundational in image generation. However, they often struggle with a phenomenon called posterior collapse, especially in VAEs, where the model ignores the latent variables and the learned representation becomes ineffective. This results in lower image diversity and quality, particularly when scaling up to high-resolution images. To address these challenges, transformer-based autoregressive models have emerged as a powerful alternative. Instead of generating an image all at once, these models produce images sequentially, pixel by pixel or patch by patch, which allows them to capture long-range dependencies and complex structure within the image. A critical innovation here is the use of an image tokenizer, which converts the continuous pixel space of an image into a sequence of discrete tokens. This tokenization is analogous to word tokens in natural language processing. Techniques such as vector quantization or patch-based encoding break down the image into smaller units, tokens, each represented by a discrete code. This representation enables the use of transformer models that naturally handle sequence data. The image generator component is usually a decoder-only transformer, which autoregressively predicts each next token in the sequence based on all previous tokens. This architecture effectively models the conditional probability distribution over image tokens, generating realistic images step by step. This autoregressive transformer-based approach has several advantages for high-resolution image synthesis. Fine-grained control. By generating images token by token, the model can better enforce consistency and details across the whole image. Scalability. The discrete token representation reduces the complexity of directly modeling high-dimensional continuous pixel values. Flexibility. The model can be conditioned on various inputs such as text prompts, enabling versatile applications like text-to-image generation. Improved fidelity. Transformers can capture long-range spatial dependencies better than convolutional models, leading to more coherent and natural images. In summary, framing high-resolution image synthesis as a sequence prediction problem with discrete tokenization and decoder-only transformers offers a promising path for generating realistic, high-quality images with controllable detail and style. In the data preparation stage, our goal is to ensure that the training dataset is both high quality and consistent, so our image synthesis model can learn from the best possible examples. We begin with image cleaning and normalization. First, we remove low-quality images. These could be blurry, have poor lighting, contain compression artifacts, or simply not match the style we aim to generate. Low-quality samples can introduce noise into the training process, leading to less sharp or coherent outputs. After filtering, we normalize images so they all share consistent properties such as resolution, aspect ratio, and pixel value distribution. This ensures that the model does not have to learn to handle unnecessary variability in the raw input format. Next is image tokenization, a critical step for transformer-based generation. In this step, we pass each image through a pre-trained image tokenizer, which converts the continuous pixel space into a sequence of discrete tokens. These tokens act like the words of a visual language, allowing our model to operate on structured symbolic representations rather than raw pixels. Tokenization reduces complexity, makes training more memory efficient, and enables autoregressive generation where the model predicts one token at a time. By the end of this stage, we have a clean, normalized, and fully tokenized data set, essentially a high-quality vocabulary of visual elements, ready for feeding into the image generation model. Our system follows a two-stage architecture, an image tokenizer for converting high-resolution images into discrete, learnable units, and an image generator that learns to produce these units autoregressively. 1. Image tokenizer, VAE. We use a vector-quantized variational autoencoder for efficient, discrete representation learning. This is essential because working directly with raw pixels in a transformer is computationally prohibitive. The sequence length would be huge, making training slow and memory intensive. A. Encoder built with a deep CNN, typically 6 to 12 convolutional layers. Uses stride greater than 1 in early layers to aggressively downsample the spatial dimensions, mapping a 1024 by 1024 image to something like 32 by 32 latent feature maps. ReLU activations after each convolution introduce nonlinearity, enabling the network to model complex spatial features. The output is a dense continuous latent representation, ZE of X, that captures high-level semantics and texture cues. B. Quantizer. The quantizer maps each latent vector to the nearest codebook embedding from a fixed set, e.g., 8,192 vectors. The nearest neighbor lookup produces discrete token indices, effectively compressing the image into a short visual sentence. This avoids posterior collapse, a common problem in VAEs, where the latent space degenerates and the decoder ignores it. Also greatly reduces the search space, since the model predicts from a finite vocabulary rather than continuous values. C. Decoder. Another deep CNN, but with transposed convolutions, aka deconvolutions, to upsample back to the original resolution. Each upsampling stage refines spatial detail, reconstructing the image from tokens while minimizing reconstruction error. The decoder is trained jointly with the encoder and quantizer, using a reconstruction loss plus commitment loss to keep the codebook stable. Second image generator, decoder-only transformer. Once we have a discrete vocabulary of image tokens, we model them with a transformer, essentially treating image generation as a sequence modeling task. A. Embedding lookup maps each token ID to a learned embedding vector. Embeddings can be shared with the tokenizer's codebook for parameter efficiency. B. Projection layer adjusts embedding dimensions to match the transformer's hidden size, e.g., 1024. C. Positional encoding. Since transformers have no inherent spatial awareness, we add 2D positional encodings flattened into a 1D order so the model knows where each token belongs in the image grid. D. Transformer blocks, stacks of multi-head self-attention layers, 12 to 48 layers depending on scale. Causal masking ensures tokens are predicted autoregressively, left to right in the flattened sequence. Attention layers model long-range spatial dependencies, useful for global consistency, such as ensuring the background lighting matches across the image. E. Prediction head outputs a probability distribution over the token vocabulary at each sequence step. During inference, we sample tokens step by step until the full image sequence is generated. Why this architecture works. The tokenization stage drastically reduces sequence length, e.g., 1024 by 1024 pixels, 1024 tokens, making high-res generation tractable. The transformer stage benefits from proven NLP scaling laws. More layers and parameters directly improve fidelity. Using discrete tokens enables cross-modal compatibility. The same framework can handle text-to-image generation simply by conditioning the transformer on text embeddings. In the model training stage, we have two major components to train: the image tokenizer and the image generator. First, for the image tokenizer training, our goal is to teach the model to convert an image into discrete tokens and then reconstruct it back with minimal quality loss. The encoder processes the input image using a deep CNN, compressing it into a lower dimensional, continuous latent representation. The quantizer then discretizes this latent space into tokens using a learned codebook, ensuring we avoid posterior collapse and keep the representation compact and stable. Finally, the decoder reconstructs the original image from these discrete tokens, again using CNN-based architectures with upsampling layers. We train this tokenizer self-supervised on a large dataset, here about 5 million unlabeled images. Since labels aren't needed for reconstruction tasks, the ML objective is to accurately reconstruct the original image from the quantized tokens. We combine multiple loss functions to optimize both fidelity and realism. Reconstruction loss, e.g. L1 or L2, to measure pixel level differences. Quantization loss to ensure stable codebook learning. Perceptual loss to align with human visual perception. Adversarial loss to encourage photorealistic reconstruction quality. Once the tokenizer is trained, we move on to image generator training. Here, we use a decoder-only transformer that takes in sequences of discrete tokens and learns to predict the next token in the sequence, similar to how large language models work for text. The training data consists entirely of tokenized image sequences produced by our tokenizer. The ML objective is next token prediction, which allows the model to generate coherent and consistent token sequences that can be decoded back into high-resolution images. The main loss function is cross-entropy loss, which penalizes incorrect token predictions and drives the model to generate more accurate sequences. Together, these two training phases enable the system to learn a powerful discrete representation of images and generate new high-quality, high-resolution visuals from scratch. In the sampling stage of our high-resolution image synthesis system, the goal is to transform a request into a complete high-quality image. This process begins with generating a sequence of discrete tokens, which serve as the building blocks of the final image. We start by randomly selecting a token from the codebook as the first token in the sequence. This codebook is learned during the image tokenizer's training process and contains a finite set of representative visual patterns. From there, we repeatedly pass the current sequence of tokens into our image generator, a decoder-only transformer. This model predicts the probability distribution over the entire codebook for what the next token should be. To decide which token to add next, we use sampling strategies. For instance, top P nucleus sampling. Top P sampling dynamically chooses from the smallest possible set of tokens whose cumulative probability exceeds a given threshold P, which allows for both diversity and realism in generated images, while avoiding highly improbable or incoherent visual features. This process continues token by token until we have the complete sequence of discrete tokens representing the image. Finally, we decode this token sequence back into pixel space using the decoder component of our image tokenizer. This decoder, built with deep CNNs and transposed convolutions, transforms the symbolic token sequence into a high-resolution image that matches the original request. By separating image generation into token prediction and decoding, we gain fine-grained control over both the creative variability and the fidelity of our outputs. and we can adjust parameters like top P or temperature to balance between diversity and precision. In this phase, we assess how well our image synthesis model performs, both quantitatively and qualitatively. Offline metrics, inception score, IS. This metric uses a pre-trained image classification model, such as Inception v3, to evaluate two key qualities of generated images: diversity and clarity. A high inception score indicates that generated images are both varied and recognizable as distinct objects. Fréchet inception distance, FID. FID compares the distribution of generated images with that of real images by measuring the distance between feature vectors extracted from a pre-trained network. Lower AFID values indicate that the generated images are closer to real images in terms of quality and diversity, making it a gold standard for image synthesis evaluation. Human evaluation. Despite advances in automated metrics, human judgment remains critical. Experts and users visually inspect samples to assess realism, artifacts, and overall visual appeal. Human feedback often captures nuances that metrics might miss, such as subtle distortions or unnatural textures. Online metrics. User feedback, direct feedback from end users interacting with the system, helps identify issues in real-world usage, such as dissatisfaction with image quality or relevance. Periodic surveys. Structured surveys provide insights into user satisfaction and preferences, offering qualitative data on how the synthesized images meet expectations. Subscription rate and churn rate. These business metrics indicate user retention and growth. A higher subscription rate suggests the product is valued, while a low churn rate implies sustained user engagement, indirectly reflecting the success of the image synthesis quality. Together, these offline and online metrics provide a comprehensive evaluation framework, ensuring the system produces high-quality, realistic images while meeting user needs and business goals. The overall system for high-resolution image synthesis is designed as a modular pipeline, where each service focuses on a specific stage in producing the final high-quality image. We start with the generation service, which is the entry point for user requests. When a user asks for a new image, say, a sunset over snowy mountains in an impressionist style, this service interacts directly with the image generator model, in our case, a decoder-only transformer. The model generates a sequence of discrete visual tokens that encode the structure, colors, and patterns of the desired image in a compact representation. These tokens are not the image itself. They're more like a compressed blueprint of what the image should be. Next, the decoding service takes over. It uses our image tokenizer's decoder to transform the generated visual tokens into an actual image in pixel space. At this point, the image has the correct content and composition, but its resolution may still be moderate, which is not ideal for professional or consumer-facing applications. This is where the super resolution service comes in. Using a pre-trained super resolution model, often something like ESRGAN or a transformer-based upscaler, we increase the image resolution while preserving sharpness and fine details. This step ensures the output meets high-quality standards for printing, large format display, or HD/4K usage. The modular approach here has two benefits: flexibility. We can independently improve or replace any stage without retraining the entire pipeline. Scalability. Each service can run on specialized hardware for maximum efficiency. For example, generation and decoding on GPUs and super resolution on TPUs or optimized inference servers. By separating concerns and optimizing each step, we ensure fast, scalable, and visually stunning high-resolution image synthesis.